Assalamualaikum warahmatullahi wabarakatuh. My name is Nurru Anida Binti Ibrahim, metric number P103512, and my paper is a review of MEMS-based micro-cantilever sensor. Okay, this is my outline of the paper. Introduction, basic working principles, concept for design of micro-cantilever and fabrication process, and then results and discussion consists of measurement results and performance evaluation, and then applications of micro-cantilever, and lastly, conclusion. Okay. MEMS, which is Micro Electromechanical System, is a driver for multiple and mixed technology integration. The micro-mechanical components can be integrated with the electronics to develop smart sensor and edge weather system with additional features such as self-test and self-calibration. In this paper, the main focus is given on the micro-cantilever-based sensor device. Micro-cantilever is a device which is capable to receive and respond to a signal, an example heat, light, motion, energy, electrical or chemical reaction can be referred to as the sensor. There are so many possible shapes for micro-cantilever like rectangular, pedal shape, triangular, trapezoidal, V-shape, step profile, I-shape, T-shape and many more. The reason for choosing micro-cantilevers based sensors are because its strong characteristic like very sensitive, fast measurement of mechanical movement and less power consumption. It also can be operated in static mode or dynamic mode based on user requirements. Micro-cantilevers also available in all sizes and its range is in length from a few meters to hundreds of meters. The micro-cantilever is a rigid beam which is fixed from one end and free from another end. The major concept is beams fixed and has a reaction force and moment created by the load acting at the free end. The purpose of the cantilever beam is to produce a bending outcome to a certain limit. Figure shows the basic structure of a cantilever, how it is fixed at one end and free from another end. According to the past research, there are few designs of micro-cantilever. One of them is by Sidaya and et al. 2019. 3 square holes of size 50 times 20 micrometer are created on a micro-cantilever at the immobile end, where piezoresistor of width 10 micrometer is placed. 72 square holes of size 8 times 8 micrometer are created along the surface with 8 micrometer gap between neighboring holes. This paper proposed an enhanced piezoresistive micro-cantilever with square-shaped stress concentration regions (SCR) at the immobile end and on the exterior of the micro-cantilever. The piezoresistor used in the simulation is p-doped semiconducting material, which is silicon. The figure shows that the design of micro-cantilever with 72 SCR. Okay, and then designed proposed by Sujay Modal et al. 2018. Geometric discontinuities, which is 3 rectangular holes of size 25 times 20 micrometer are created on a conventional rectangular micro-cantilever at the fixed end, where the zigzag shape piezoresistor p-doped silicon of width 10 micrometer and depth 0.2 micrometer is placed. 40 square holes of size 10 times 10 micrometer are created along the surface of the micro-cantilever with 10 micrometer gap between adjacent holes. And then in the paper by Shukla KK, Mathumanikam T and Sheila T 2019, a shaped rectangular structure has been chosen and dimension taken as length 500 micrometer, width 50 micrometer and height 10 micrometer using silicon nitride as a material. Okay, for the fabrication process, Surya Srikant et al. 2020 in their paper designed and simulated a rectangular MEMS cantilever with dimensions of 225 micrometer times 80 micrometer times 2 micrometer. The fabrication process of the analytical design and FEM simulations of the piezo-resistive cantilever was using IntelliSuite. The fabrication process flow is performed by deposition. Lithography and etching were done on rectangular cantilever beam. Silicon wafer is utilized as the underlying layer on which thin film is grown. Thin film have been utilized to construct both active and passive part of a large entity to adjust the geometrical properties of a device layers. The impurity might be presented for thermal diffusion. Then the outline of underlying layer is transferred onto the thin film by a piezo-resistive substance called photoresist. After the pattern generation, the selective removal of unnecessary regions of underlying layer for outline formation, then wet etching has been used in etching process. Etch mask piezoelectric material is utilized in the removal process to selectively prevent portions of the material being engraved. Okay, and then for Amiri IS and Andaki S 2018, the micro cantilever array was simulated using COMSOL Multiphysics 4.2 and ANSYS environment. The fabrication of the cantilever was done on a single-side polished N-type SOI wafer of 100 crystallographic directions. The following steps were involved in fabricating the design, which is silicon wafer cleaning, spin coating, photolithography, optical inspection, dry etching, photoresist removal, wet etching, optical inspection, and critical point drying, evaporation, and lastly, evaporation process. Okay. For the measurement results and performance evaluation, Amiri IS and Andaki S 2018 explained that the micro cantilever before and after ozonation was analyzed by laser Doppler vibrometer (LDV) to determine the responses such as quality factor along the frequency and deflection. The responses such as the deflection and frequency vary for each cantilever in a micro cantilever array with ozone concentration. From the experiment, it can be clearly understood that by decreasing the dimensions of the cantilever, the deflection and frequency shift decreases. And then by Sri Surya Srikanth et al. 2020, the finite element method analysis is done using IntelliSuite software. There are two simulations in this paper. For the first simulation, the length is varied with the width. Thickness of a cantilever is kept constant. It was observed from the FEM simulations that as length increases, deflection also increases. And then for the second simulation, the thickness varies. The width length of cantilever is kept constant. It was observed from the FEM simulations that as the thickness increases, deflection also decreases. Okay, there are a lot of applications of micro cantilever. One of them is a biomolecular detection. Okay. Micro cantilevers with nanomechanical deflections are applied to the detection of biomolecular agents. And then the concentration of different kind of analytes that is present in human blood can be reported by using micro cantilevers. Cantilever-based biosensors have been extensively used in protein detection in ultra-low concentrations in several different applications such as prostate cancer detection, myocardial infarction, and also protein conformation. Microcantilevers also have been used widely in DNA detection. Microcantilever also have been used for sensing application in physics and chemistry. They can be used to measure sound wave velocities, fluid pressures, and flow rates, and can be tuned to selectively pick up acoustic vibrations. Biotoxins could be detected with sensitivity at the peptide level by coating one side of the cantilever with monoclonal antibodies specific for the particular biotoxin. It has been observed that silicon nitride cantilevers coated with gold on one side are quite sensitive to pH changes. So, based on this, cantilever-based sensors can be made to detect the pH change. They have also been used to detect mercury vapor, humidity, natural gas mixtures, toluene, and lead in water. Okay, for the conclusion, micro cantilevers have got potential applications in every field of science, ranging from physical and chemical sensing to biological disease diagnosis. Through this paper review, design and analysis had shown the importance of shape, size, and selection of materials while designing a micro cantilever-based sensor. The major advantages of employing micro cantilevers as sensing mechanisms over the conventional sensors include their high sensitivity, low cost, low analyte requirement, non-hazardous procedure with few steps, obviating the need for levels, of course, quick response and low power requirement. The technology has been developed in the last few years for the fabrication and use of nano cantilevers for sensing applications, thereby giving rise to nano electromechanical system names. That's all for my presentation. Thank you very much.